The EM1501 electromagnetic-acoustic thickness gauge measures the thickness of a metal object and displays the result on the screen. We see the thickness value in millimeters. When the test object does not have any special features, for example, it is quite a smooth sheet or pipe, then this thickness value is usually enough. When measuring the thickness of heavily contaminated or rusted objects, objects made by casting, or objects with special external or internal geometric or material characteristics, the use of a scan may be required to obtain reliable measurements. Let's switch the device to the A-scan display mode. The horizontal axis displays the timescale, which is converted into millimeters by multiplying by the value of the speed of sound in metal. The vertical axis displays the amplitude of the signal received by the device in percent. In the left part of the A-scan, there's a very high amplitude signal, which is caused by the pulse created by the generator of the device itself. This area is called the dead zone, since no echo signals can be observed in it. Next, we see the useful signal, as well as noise. Let's switch the graph to the A-scan envelope view mode for a better visual display. If the transducer is too far from the test object, then to the right of the dead zone there is only noise, without useful bottom signals. The device cannot measure the thickness of the test object if the transducer is too far from the test object due to the thickness of the coating or rust. As soon as we bring the transducer to the test object at a distance sufficient to form and receive an acoustic wave, bottom signals appear on the A-scan by which the device begins to measure the thickness. Accordingly, when operating with the device on complex test objects, it is necessary to monitor the level of bottom signals on the A-scan. If the test object has plain parallel surfaces and is not heavily corroded, then there usually are smoothly fading out alternating echo signals on the A-scan. The acoustic wave emerges at the surface of the test object, reaches the opposite surface of the test object, reflects and returns to the same point from where it has emerged. Then the wave moves between the surfaces of the test object until it damps. But in the presence of severe corrosion, this process changes. For a given 8 mm thick object, we can find areas where the regular A-scan shape turns into an almost random signal. Corrosion of the opposite surface of the object leads to reflection of waves in random directions. We can conclude that there's a defect in the test object, which unfortunately prevents us from taking measurements. If there are no clearly defined alternating bottom signals on the A-scan, it is recommended to move the transducer slightly in any direction and try to find a place where bottom signals are clearly defined without a strong interference pattern. In addition to corrosion, the shape of the test object can interfere with the thickness measurement process. This can be demonstrated on the following sample. The device detects only noise, since the wave, reflecting from the lower surface of the object, spreads sideways due to the geometry of the object. Only in the center of the object we can see the echo signal by which we measure the thickness. As noted above, for the correct operation of the device, it is important to observe echo signals on the A-scan. But there are situations when the automatic thickness measurement mode does not operate correctly due to the presence of different confusing echo signals on the A-scan. For such cases, the device provides 2 additional measurement modes for manual operation. These are modes for calculating thickness using 1 or 2 gates. Let's consider a pipe with a thickness of 3.8 mm. We do not see the first echo signal, since it is in the dead zone. Based on the second and third echo signals, the device correctly measures the wall thickness. But in some sections of the pipe, the third and fourth echo signals suddenly drop almost to the noise level. The device detects only 1 echo signal, which is in fact the real second bottom signal, but the device considers it the first and calculates the thickness incorrectly, doubling the real value. This effect can occur due to the anisotropy of the metal, when transverse waves with different polarizations can propagate between the walls and at different times, and at some points add up and neutralize. Manual measurement mode using 2 gates allows us to take the 5th and 6th echo signals as a basis and correctly measure the thickness value at this point. Let's consider another case. The first echo signal is in the dead zone. At some points on the surface, other echo signals are close to the noise level. By moving the transducer a little at such a point, we will see all the echo signals, but they remain at the noise level, and therefore the device readings are constantly changing. In this case, we can manually set the gates on the 2nd and 3rd echo signals and achieve correct device readings. Now let's look at a sample with a small hole. Suppose that we are measuring the thickness of an object, and for some reason we are not interested in the hole detection, but we need to measure the distance to the bottom surface. We see the main echo signal on the A-scan by which the thickness of the object is measured. In the area of the hole, there is both a signal from the hole and a signal from the opposite surface on the A-scan. Of course, the device does not have information about what exactly we are measuring and displays the minimum thickness. In this case, the manual measuring mode will come useful again. This time we will use 1-gate mode. Let's place the first gate in the area of the bottom signal. The device now takes into account only the signal in the zone limited by the gate, therefore it does not react to the echo signal from the hole. This method of taking into account only certain selected echo signals is well suited for inspection of thick but heavily corroded test objects, as well as products made of cast iron or other cast products, since when testing such products, there are parasitic interfering echo signals due to the coarse grain structure. In conclusion of the video, let's consider another useful A-scan tool adjusting the number of averages used by the device. Here we see noise leading to unstable measurement results. Let's increase the number of averages. The measurement time will increase, but the reliability and accuracy of measurements will increase too. A scan is an effective tool for an experienced non-destructive testing specialist.